unfold.
So back in 2022, the Nobel Prize in Physics wasn't just for some new discovery. It was really for a demolition. A prize for proving that our most basic, common-sense idea of how the universe works is just wrong. And it's a discovery so profound, we're still trying to wrap our heads around what it all means. So how did we get here? And what's it like to live in a universe without a solid, objective reality? Let's dive in.
Okay, so to really get this revolution, we've got to first understand the Old Kingdom, right? The world that Albert Einstein fought so hard to defend. It was a world built on what he thought were just these unshakable, totally intuitive principles.
And this quote, man, it gets right to the heart of it. For Einstein, reality was objective. The moon, a planet, a ball rolling across the floor, they exist, and they have all their properties whether we're there to see them or not. This idea was the absolute foundation of his entire worldview.
He called this first principle realism. And it's a pretty simple idea, right? It's the belief that when you measure something, you're just revealing a truth that was already there. When you check where a ball is, you're not creating its position, you're just discovering it. It's simple, powerful, and it feels completely right.
The second pillar was locality. This basically says that nothing can affect something else faster than the speed of light. An event happening right here can't instantly influence an event way over there. There's a cosmic speed limit. Anything else, well, Einstein famously just dismissed it as spooky action at a distance.
So this whole battle for the soul of physics, it kind of boils down to a fantastic analogy. Is the universe made of things with fixed predetermined properties like a pair of gloves? Or is it made of something much, much weirder, something more like spinning coins?
Okay, so this lays out the two competing ideas perfectly. On one side, you've got Einstein's gloves model. Imagine you pack a left and a right glove into two separate boxes. You mail one to Tokyo. When you open your box in New York and see a left glove, you instantly know the other one is a right glove. That rightness was always there, just waiting to be revealed. But the quantum spinning coins model is way stranger. Here, two entangled coins are spinning, and they exist as this probabilistic blur. They're neither heads nor tails. The moment you measure one and it becomes heads, the other one, no matter how far away it is, instantly becomes tails. The property wasn't revealed, it was created right on the spot. Einstein hated this, and for decades it just seemed like a philosophical argument we could never settle.
But then, a physicist named John Bell came along and did something, well, extraordinary. He figured out a way to take this philosophical duel between gloves and coins and turn it into a mathematical test, a real experiment you could actually go out and do. Bell's logic, if you simplify it, is kind of like a game. Imagine Alice and Bob can't talk to each other. They have to create a script beforehand, a little cheat sheet that tells them how to answer 3 potential questions. This script, this cheat sheet, is like Einstein's hidden information, the pre-existing properties. The whole point of the game is to see how often their answers match up when they're asked different questions.
And here is the crucial point. Bell calculated that no matter what pre-written script Alice and Bob use, if they're living in Einstein's glove universe, their answers when asked different questions must match at least 1/3 of the time, 33%. Now this isn't a guess, it's a hard mathematical limit.
But here's the bombshell. Quantum mechanics predicted something else entirely. It said that if you did this experiment with entangled particles, the match rate would only be 25%. That's way lower than the 33% minimum. It's a number that a glove universe, a universe with those pre-existing cheat sheets, simply cannot produce. All of a sudden, we had a testable contradiction.
And this chart illustrates the real-world version of the test, which is called the CHS-H inequality. It sets a hard limit for any local realist universe at a value of 2. Anything above that is impossible. But just look at the quantum prediction, 2.82. The two theories weren't just a little different, they were in violent disagreement. All that was left was to build an experiment and ask nature itself which one was right.
And that question, well, it sparked an incredible 50-year quest. It took 3 brilliant, incredibly persistent experimentalists, each one building on the work of the last, systematically closing every single possible loophole, until there was absolutely no escape from the conclusion.
It all started in '72 with John Clauser, who built the very first Bell test and got a result that lined up with quantum mechanics. Then, a decade later, Alain Aspect closed a major loophole, making sure no hidden signals could be coordinating the results. And finally, Anton Zeilinger performed the ultimate test,
using light from deep space to rule out even the most bizarre cosmic conspiracies you could think of.
What's amazing is the sheer ingenuity here. Clauser literally built his first experiment with duct tape and spare parts at a time when senior physicists were telling him he was wasting his career. Aspect invented these ultra-fast switches that could change the measurement settings in just nanoseconds, faster than light could even travel between his detectors. And Zeilinger's experiment is just mind-blowing. He used the light from quasars billions of light years away as his random number generator. This made sure that the choice of what to measure was made before the Earth had even formed.
So the experiments are done, the verdict is in. Einstein's glove universe is dead. What does that mean for us? I mean, what kind of universe do we actually live in?
Well, the conclusion is inescapable. The universe is not locally real. And this forces us to choose between two equally reality-shattering options. Either we ditch locality and accept that influences can happen instantly, faster than light, which would violate relativity. Or we ditch realism and we accept that the moon really might not be there, or at least not in a definite state when no one is looking. For the most part, physics has chosen to abandon realism.
A really powerful way to think about this is like a video game. To save processing power, a game engine only renders the graphics that are right in the player's line of sight. Everything else just exists as data, as potential. Well, these experiments suggest our universe works the same way. It doesn't calculate the definite state of a particle until an observation forces it to. Reality, it seems, is rendered on demand.
And this leads to an absolutely astonishing idea from the physicist John Wheeler, summed up in this phrase, it from bit. It suggests that the most fundamental currency of the universe isn't matter or energy, it's information. That every particle, every force, gets its very existence from bits, from the yes or no answers generated by acts of observation.
And that, of course, leaves us with the ultimate question. If the universe waits to be seen before it decides what to be, if reality is only solidified by the act of observation, who or what is doing the observing? It's a question that takes us from the very edge of physics to the heart of philosophy. And honestly, it's a mystery we've only just begun to explore.